Hello dear students, welcome you all. In this lecture, I am going to discuss about the next type of A to D converter. You can see here, this A to D converter is, successive approximation type A to D converter. So, in the previous lecture, I have discussed about the counter type, right? Counter type A to D converter. And we have seen that this counter type A to D converter was suffering from a major drawback, and the drawback was the resolution time, right? I have explained there in that lecture that in the worst case, this counter type A to D converter can take 2 raised to power n cycles, clock cycles, right, for the conversion. Here n is the number of bits used for representing the corresponding digital signal, right? I mean the output digital signal. So if I am using 4 bits, then in the worst case it can need 16 cycles for the conversion of a given analog signal, and it was a major drawback, right? So now in this successive approximation type of ADC, you can see here the circuit schematic diagram that I have drawn here. This drawback has been removed. Now you might have remembered that what was the reason for that drawback, long resolution time. The drawback was that every time after comparison, the counter was starting from 0, right? So that was a big problem, right? And I had told you at that time also that if we can design a circuit that can start not from the 0 but a very close value to the previous value, right? In that case, the time taken for the completion will be small as compared to the counter type. So this successive approximation work on this principle, right? Every time when it compares the corresponding digital output with the input signal, and then after comparison, if the input signal is more than the generated this digital signal, then in that case it will start from not from 0 but it will start from the next value that is close to the input signal. So you will see when I will explain in details by taking a suitable example that how this will work, right? So first of all, look at the schematic diagram. This is the input voltage, that analog input voltage that we are going to convert into the corresponding digital signal, and in this case I have taken it as a 5.2 volt. You can see here this is a sample and hold circuit, right, which is taking the samples of this input signal after regular interval of time. This is a comparator circuit. You can see here this is in 1 terminal, 2 terminal and 3 terminal. One input of the comparator is coming from the digital to analog converter, right? This is the one input to this comparator, and other is the input signal that is coming from the sample and hold circuit, right? So in nutshell, we can say that this comparator is doing the comparison between the input voltage and the output generated by this DAC converter, right? Here we have taken a DAC converter of 4-bit, right? I mean we are considering a 4-bit digital output, right? This is successive approximation resistor circuit designed for doing this task. It is a control circuit, right, that gives a control command to the SAR for increasing or decreasing the digital output that is going at a D to A converter, right? This is the reference voltage applied to the D to A converter, 10 volt. Now you will understand it better when I will take the example. The example here given is a 5.2 volt. Now when this circuit is switched on, initially the we have now taking 4 bits, 1, 2, 3, 4. This is the MSB, right, and this is the LSB. Now when the circuit will be switched on, the first output, digital output, that is generated by this successive approximation resistor it will be 1 0 0, means the MSB will be set to 1, right? First of all, MSB will be set to 1. So when MSB is set to 1, you can see here it is set to 1. So the output is 1 0 0, means the output of this SAR circuit. Now this 1 0 0 output is sent to a digital to analog converter, right? Now we know very well what is the output of a D2A converter. It is equal to 2 raised to power 0 B0 plus 2 raised to power 1 B1 plus 2 raised to power 2 B2 2 raised to plus 2 raised to power 3 B3 divided by 2 raised to power, and you might have remembered the conversion of D2A that I have discussed in the starting lectures of this unit. It was 2 raised to power 0. I wrote it to 0. So let's correct it. It was 2 raised to power 0. Right. Now here 2 raised to power 3 B3, V3 is for MSB bit. So in this particular case, this and these B0, B1, B2 all are 0 0 0, but this is B3 is 1 corresponds to 10 volt, right? So because in this D2A converter, 1 is equal to 10 volt and 0 is equal to 0 volt. So when you will convert it, you will get 0 0 0 into 8 into 10 divided by 2 raised to power n, 4 bits, so 16. So it will give me 5 volt, right? You can see here 5 volt BDC, right? So now, as I told you that this output is 5 volt. Now this 5 volt is applied here. It is compared with this, 5.2 volt. So obviously 5.2 volt is more than 5 volt, right? So according to that, I will get the signal at this output that will be obviously high, right? Because the input at this terminal is high, so output will be, we can say 1, right? Logic 1 or high, right? So if it is 1, then this control circuit will send a signal to this SAR, and now in that case what will be the output of this? Now the next bit is initially it was 1 1 0 0, so now it will become 1 1 0 0. Why? Because the input generated by previous input generated by this SAR was less than this one, right? So now obviously this will be increased, so it is 1 1 0 0. So now 1 1 0 0 will appear at this point, right? Now when 1 1 0 0 will appear at this point, you can see what is the corresponding value. So 1 1 0 0 means now 1 1 0 0. So in that case, what I will get? You can find the value, right? It was 4 2 raised to power 2 4 into 10 plus 8 into 10 divided by 16, right? So 80 plus 40 divided by 60, 120 divided by 60, right? So you can simplify it. It will become 7.5, right? So when you will compare this 7.5 here, now this will become 7.5, right? So 7.5 when it will go to here, right? Obviously now 7.5 is more than 5.2. Now this output, now here this input is now high, it will become low, right? So you can see here now as I told you that 7.5 volt is higher than 5.2 volt. So the earlier generated output by the SAR was 1100. Now the other option that it can generate is 1110. But when it will generate 1110, it will even more than this voltage, right? So it means this is dropped. But SAR will do. SAR will make this bit as 0 and it will proceed to the next bit. I mean, it will generate now, right? It will generate now 1010. It means this bit, it is now made 0 and next bit is set 1010. Now when it is set 1010, right, what will be the corresponding output? We can find the corresponding output simply by applying this formula and it will come out to, I am writing it directly, 6.25 volt, right? Again the same thing, 6.25 volt is here, 6.25 volt, it is more than this. It means again it is more, it means the thing is not going to settle. This bit is not going to solve the purpose. So now first of all look at this, right? This was 1010 that I have made here, right? What is the next higher bit than this? The higher possibility than this is 1011. It can be there, right? If this voltage was less than this one input voltage, right? If 6.25 volt was less than, suppose it was 7.2 volt, right? For example, in that case, this SAR will have progressed in this direction toward this side. But as this is less than this value is higher and this is low. It means it will progress toward the lower side, right? This value is dropped, right? Now where it will go? It will go 1 0 0 means this bit will be set to 0 and 1, right? Here I will get now 1001. This bit is set to 0 and this is set to 1, right? Now what is the corresponding output? It is 5.625 volt. You can calculate it by using this formula, right? Now if you look at this 5.625 volt, right? Again this value is higher than 5.2 volt. Now what, right? Once again I am repeating, this value can even go if this value was less than this, right? Imagine this value was less than this, then this would have progressed in this way 1010. But as it is not allowed because this value is higher than this, so it will go toward what is the possibility lower than this? The possibility is this bit will become a 0, 100. Now this bit and this corresponds to 5 volt. It means this is the nearest approximation of this voltage that is given at the input, nearest approximation. But you can ask a question that in the beginning this has generated 5 volt, right? Then why we get stopped here? The converter will not stop here. It will try all the possibilities, right? And in the end, when we reached at this point, it means this is the nearest possibility, and now we can't go further this, right? 5 volt is the lower than this one. Now we are from higher side, we are going to the lower side because 5 volt is now less than 5.2 volt. So we have two possibilities. We have to pick this one or we have to pick this one. These are the two possibilities, right? So this is the correct conversion. So this is the way of converting this number. Now I have shown the different steps. You can see here, right? For all the possibilities. Initially the MSB was set as at 1. Now the possibility BDAC is greater than B input, and the lower side is less than or we can say B input is greater than BDAC. Right? So you can see here, if it is greater than this, right, DAC is greater than this, then we will proceed to the next bit by setting this to 0, right? This one. Now again at this stage, again we will do the comparison. If this the output corresponding to this digital number is higher than B input, then we will go to this one. But if it is lower than B in, we will go toward this side, right? Again here the same logic is there. BD is less than B in, and here BD is greater than B in, right? BD is greater than B in, then we will go to this side, and if it is less than, then we will go to the this side. If it is higher, then this bit will be set to 0, next will be set to 1, and if it is less than V in, then the value will be increased. I mean, then we will get 0, 1. This bit will also set to 1. Again, here we will do the comparison. If same thing, BD is greater than V in, the next bit, this will be set to 0, and next bit will be set to 1. But if it is higher than V in, then this bit set to 1, and this bit also is set to 1. So in this way, you can see all the possibilities that corresponds to 4-bit number, they has been tabulated here. 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, right? 15 is the last from 0 to 15. Total 16 possibilities are there. So we can reach at any of the possibility starting from here. But you can see here now how many number of steps are required. This is the first, second, third, and fourth. Fourth, you can go either this side or this side. It doesn't matter. Let's go toward this side, right? 1, 2, then 3, then 4. If I'm going toward this side, 3 and then 4. So in all the cases, the maximum steps, maximum clock cycles that are required for the conversion is equal to 4, and 4 is equal to number of bits in the digital output. It means the conversion time TC, that is equal to number of bits multiplied by the clock time. So this is the time required for this conversion. You can see all the possibilities are given, and this is the big advantage. Now in this case, in this type of converter, we don't have to start from 0 every time, because when we will be here, we will just look at the adjacent values to this number. We will not go to that here. But in counter type A to DC, we were starting from here every time. This was the drawback, right? But here we are doing only the approximation to the next value, nearest value, right? So this is the big advantage of this, that the time required for the conversion depend upon the number of bits, and it is the worst case, right? Otherwise it can be less than this. What in the worst case, it will be equal to number of bits, I mean 4 multiplied by the clock time, right? So this is the advantage. In earlier case, this time was very large required time. So this is the working of this successive approximation type A to D converter. As far as its advantages, disadvantages are concerned, advantage is this one, that the time required is low, and this circuit make these conversions easy. But the drawback side is that these circuits are very complex to design, right? This is the complexity of this circuit that makes it's a drawback, right? So this is all about this successive approximation type A to D converter. As far as applications are concerned, it is commonly used in all A to D converters because of its low conversion time, low power consumption, high accuracy, right? But still it has one drawback that I told you. So this is all about it. So thank you very much.